we kind of have gotten ourselves into a little bit of trouble with our definition of a linear map because it's just so abstract. It's kind of hard to know what it all means. And in particular, if you have two finite dimensional vector spaces, it's kind of, we know sort of on general grounds that there is a vector space of linear maps between those vector spaces, so from V to W, but it's we have sort of so many layers of abstraction to build this thing up that it's kind of hard to understand exactly what the vector space of linear transformations from V to W would even look like. So what we're going to do is put some effort into understanding what this vector space really is for a given V and W. And I'll kind of spoil the surprise here. What we're going to do is for every linear map from V to W, what we're going to do is associate with it in some mechanical way a big matrix of numbers, and we'll come up with this correspondence in a way so that it's a one-to-one correspondence. And in fact, even better than that, matrices of a certain size already have a vector space structure. We've been calling this M sub Mn, and what we'll see is that the vector space of linear maps from V to W is actually isomorphic to one of these guys in sort of a very natural way. The tricky part will be figuring out exactly how do we construct this correspondence between linear maps on one hand and matrices on the other. And it's going to be a multi-step process. So the first thing that we're going to do is figure out if we have a linear map, how can we represent it nicely as a matrix? And then, in the next section, we will do the reverse. We'll see if we have a matrix, how it represents a linear map. And when we have both directions set up, then we'll see clearly that it's a one-to-one correspondence, and in fact it will also respect the vector space structure. So really what we're doing here is we're going to construct a vector space isomorphism between this vector space and this vector space for certain values of m and n, right? What m and n are will depend on what these vector spaces are. So what is the big picture of coming up with a matrix that represents a linear transformation? So suppose you have a linear transformation, how do we associate a matrix with it? Well, a linear transformation is a map like this, right? So F is something that takes us from V to W, and the thing about V and W is we're working at a level of abstraction where we don't really know what V and W look like other than that they're finite dimensional. So, we just don't really know what would make sense to put into this matrix. But what we can do is, because V and W are finite dimensional, we know that they are isomorphic to certain Euclidean spaces. So we know that there's some Euclidean space that is isomorphic to V, we'll call it Rn, and we know there's another Euclidean space that's isomorphic to W, we'll call that Rm. So again, I'm foreshadowing with what these m and n's will be. But how do we construct a nice isomorphism from V to Rn? We've actually done this before, and the way that we've done this is for V, we choose a basis, B, say, and once we've chosen a basis, we automatically get an isomorphism from V to Rn, and we've been calling this rep B. So rep B is the map that, right, if our basis is beta 1 up through beta n, right, there has to be as many basis vectors as there are dimensions in this space. Rep B is the map that takes A1 beta 1 up to A n beta n. Rep B maps that to the vector a1 down to an. Right? And we'll do something similar over on the w side. We'll have a basis which we'll call D, of vectors, say, gamma 1 through gamma m. And that produces a map rep D that maps, say, b1 gamma 1 plus dot 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 plus bm gamma m to the vector b1 down to bm. So then the trick to constructing a matrix that corresponds to F in some sort of nice way is to somehow fill in the gap here, right? So we already know how to get an isomorphism on either side. The question is, how do we come up with a matrix that sort of somehow represents F once we've switched to these Euclidean spaces? And to get an idea for how that works, we're going to start with an example.